this is a sphere of positively charged of density sigma, and it is also a positively charged of density rho. This is your hollow sphere. When your sphere is hollow, it can be named as conducting and non-conducting, both. Okay, conducting and non-conducting. Sometimes it is also called solid conducting sphere. Solid conducting sphere. Similarly, this is another sphere which is known as the solid non-conducting sphere. Solid non-conducting sphere. Okay, note it down, please. Note it down. All of you have noted it?
Wait, sir.
Sorry?
Wait, sir. We're still right.
Okay, okay.
No, sir.
Good. Nawal, have you noted it?
Yes, sir.
Okay, good. And now we are going to discuss about the electric field due to hollow. Hollow is also known as the conducting sometimes. Sorry. Conducting or non-conducting for both. Okay. Or solid conducting sphere. This topic can be asked in your exam by the by these three names. It may be electric field due to hollow. This is nothing. Okay, due to hollow, conducting, solid sphere, or conducting sphere. Sometime it may be called as conducting sphere. It may also called as non-conducting sphere, or sometimes it is also known as the solid conducting sphere. So for all of these three names, okay, your solution will be same. Okay, note it down. Electric field due to hollow, non-conducting or solid conducting spheres. Okay, we have taken as a sphere here at this position. This is our sphere of positively charged. Sphere of positively charged of radius r. This is your positively charged sphere. Okay, and we are going to calculate the electric field due to this sphere. So first of all, we can write here, consider a sphere. One second. Consider a sphere of radius r, and having charge capital Q. Having charge capital Q. All right. And now we are going to calculate the electric field due to this sphere. The first one is outside. We are going to calculate electric field outside of the sphere. Okay. To calculate the electric field outside, first we are going to draw the diagram of this sphere like this, having radius r. I mean capital R. This is your radius of the sphere. And we are going to calculate electric field at any other point P. This is a point P where we are going to calculate the field. To calculate electric field at this point P, first of all, we should draw a Gaussian surface which is passing through this point. Then what will be your Gaussian surface here? This is your Gaussian surface which passes through this point P. Okay? Which is passes through this point P. And now let's consider that the radius of this Gaussian surface is r. I mean small r we are taking here. This is your small r. And what is the direction of electric field? Electric field lines always be perpendicular to the surface in away direction. Why? Because the sphere is positively charged. This is your direction of electric field. If it is the direction of electric field, we can consider it just like an area vector, an area of ds, and the area vector of this will be n cap, or you can also say s cap. Okay, this is your area vector. Now, what will be the flux? First of all, we will we will calculate the flux. Then by calculating flux, we can easily find out the electric field, okay, due to this sphere. Now, we can mention here, consider a Gaussian surface of radius r. This is your radius r. Then what will be the flux through sphere? What is the flux through sphere? The flux is phi is equal to integration of E dot ds. We have already know the angle between E and area vector is 0 degree. So we can put here phi is equal to E integration of ds cos of 0. And finally we can write phi is equal to E into integration of ds will be s. S is your total area of the sphere, and the value of total area of the sphere is 4 pi r square. Okay, this is the amount of flux passing through this Gaussian surface. Okay, and now for calculation of electric field, we should use the relation of the flux and the flux and the charge. Flux and the field. So we can write here using Gauss law. Using Gauss law, we know phi is equal to Q enclosed over epsilon naught. What is your phi? Phi is the E into 4 pi r cube. And Q, what is the Q here? Q is your Q. Okay, there is no change in the Q over epsilon naught. Finally, we can say E is equal to E is your electric field, which is Q over 4 pi r square epsilon naught. Are you clear or not? This is the total electric field produced due to this charged sphere. Okay, due to this charged sphere. Note it down, please. In terms of density, if you want to write it in terms of density, we have already know for your surface charge density, sigma is Q over total area. We can also write sigma is, Q is equal to, we can write here Q is equal to sigma into what is your S? S is your 4 pi r square. You can put this value in the equation number 2. You get E is equal to sigma 4 pi r square over 4 pi r square epsilon naught. This whole part 4 pi r square and 4 pi square will cancel each other. Finally, you get E is equal to sigma over epsilon naught. This is the equation of electric field in terms of density sigma. Okay. Sorry. Just 1 second. 1 second, please. There is a big mistake. 1 second. Yeah, surface charge density is available for radius capital R. So you should write 4 pi capital R square. 4 pi capital R square. Okay. And now you can put this value. Put value of Q in equation number 2. We get E is equal to sigma 4 pi capital of R square over 4 pi small r square epsilon naught. 4 pi and 4 pi will cancel each other and you get E is equal to sigma over epsilon naught r square over r square. This is the electric field, value of electric field due to this sphere, okay, on outside in terms of density sigma. Are you clear or not? Hello?
Yes.
Yeah, all of you understanding this equation?
Yes.
Yeah, we can mention it equation number 3. This is the equation number 3 you can take. Note it down, please. Have you noted it? All of you have noted it or not?
Yes, sir.
Okay, good. This is the value of electric field outside of the sphere at any point P, you can say, which is at small r separation from the center of the sphere. Okay. And now we are going to calculate the electric field at the surface of the sphere. So in part 2, we are going to calculate at the surface. At the surface. For surface value, it is very, very easy to calculate here. Just you can take easily an sphere of charge plus q sphere of charge plus q. Okay. And now the radius is already capital R once again. And we are going to calculate electric field at the surface of this sphere. You can say here, I mean at this point here, you can consider here. Okay. If you want to draw a Gaussian surface, then we can consider that the Gaussian surface is passing through this point, okay, by touching the surface of the sphere, just like this. This is your Gaussian surface, you can say, okay, which is typical to see here. This is your Gaussian surface, which is which also touches the the surface of this sphere, okay. If the Gaussian surface is touches the sphere, then we can say the radius of this Gaussian surface small r is equal to the radius of the sphere capital R. Are you understand, Nawal?
Yes, sir.
Okay. Hence, first of all, in the first step, what we should calculate here? Can anyone tell me electric field or flux? Electric field or flux? What we are going to calculate? We are going to calculate flux because Gauss law never calculate electric field directly. It calculates flux. Then by the help of that flux, you can calculate electric field. Are you clear?
Yes, sir.
So in the first step, we should calculate flux through a sphere. What is a flux through a sphere? It is again phi is equal to integration of E dot ds cos 1 second. What will be the value of electric field? And suppose that we are taking this area a vector here, and the direction of the electric field is perpendicular to the surface, which is passing like this because it is a positively charged sphere. And what will be the area vector? Area vector is along this direction. Hence, again, we can say the angle between E and area vector, I mean, the electric field and area vector is 0. So we can consider here cos 0 degree, and phi will be integration of 1 second. Phi will be by taking E outside, integration of ds. After integrating, you get S. You get S. Phi is equal to E into S. What is your total area? Total area is E into 4 pi R square, which is capital R square. Okay. Because we have already considered here R is equal to capital R. Now this is your electric flux passing through this Gaussian surface. Now if we have flux, then we can easily calculate the electric field through this sphere at the surface. Your electric field will be, electric field is phi is equal to Q enclosed over epsilon naught or you can say Q enclosed is equal to 1 second. No need to expand here. You can put here directly the value of phi E into 4 pi r square is equal to Q enclosed is your Q over epsilon naught, and E will be Q over 4 pi epsilon naught r square. This is your value of electric field due to this conducting sphere at the surface. Note it down, please. In terms of density, if you want to calculate, your equation will again be sigma is equal to Q over F. So your Q will be is equal to sigma into S. Your S is 4 pi r square, because r is equal to the capital small r. When you put this value of Q into this equation, you get E is equal to sigma 4 pi r square over 4 pi epsilon naught r square. 4 pi r square cancel with 4 pi r square, which is E is equal to sigma over epsilon naught. This is your value of electric field at the surface of this sphere. Okay. Note it down, please. This is your part 2. I mean, at the surface, field at the surface. Have you noted it?
Yes, sir.
Good. Next one is inside the sphere. Inside the sphere. Okay. This is our next part. Now, let's consider this sphere again. And this is of radius r, having positive charges. And we are going to calculate electric field at any point inside this sphere. Suppose that I am taking this point here. When you are going to take this point, then you should draw a Gaussian surface which passes through this point like this. Are you clear? The radius of this sphere is small r. If this is small r, then can anyone tell me what will be the value of flux? Your flux is phi is equal to Q enclosed over phi is Q enclosed over epsilon naught. And we have already known this is your conducting sphere. If this is your conducting sphere, then there is no any charge is available inside this sphere. Okay. So we can write here Q enclosed is 0. When you put this value into the above equation, you got phi is equal to 0. If the flux inside is 0, then we can also say electric field inside must be 0. Hence, we can also know, or we can also say electric field at center is 0. Okay, note it down, please. Have you noted it?
Yes, sir.
And now we have three values of this. The first one is at the surface, sorry, outside. The value of outside is sigma r square over r square. You can take it. We can put it here. E outside is sigma r square over epsilon naught r square. And electric field at the surface is sigma over epsilon naught, and electric field inside is 0. These are three values of electric field at different positions, okay, due to this sphere. Now, what will be the graph for this? First of all, try to understand carefully here. We are taken here, this is sphere like this. This is our sphere, okay? And the center of this sphere is of radius r. This one is the center of this sphere, radius r, capital R. If we draw a coordinate frame with respect to this, then we have okay. Try to understand. This is the point, sorry, this is the line which touches the surface of the sphere, okay? And we have already know inside of this sphere, electric field is 0. This means if you are taking any point inside this sphere, electric field will be 0. Are you clear? Causing which there is no any graph is possible here. But when you are reaches from center to the surface of this sphere, you have sigma over epsilon naught. Then we can draw a line here which represents sigma over epsilon naught. This is your line which lies at r is equal to capital R. I mean, small r is equal to capital R. This is the position where small r is 0, and this is the position, I mean region, where small r is less than capital R. At this position, r is equal to 0. We have already know from 0, from when r is equal to 0 and r is less than r, for both of these conditions, your electric field will be 0, because these conditions lies inside this sphere. Okay. When we reaches at small r is small r is equal to capital R, this is the position of the surface. I mean, we have reached at the surface of this sphere, and at the surface of the sphere, we have some values of the electric field, which is sigma over epsilon naught. Okay. This line represents sigma over epsilon naught. But when you go away from this surface in the sense we are dealing the condition of outside, I mean, we are discussing for this position here now. So in this position, we can look at here, E is inversely proportional to the R square, which is small r square. Then we know for E is inversely proportional to R square, the graph will be hyperbola. When you draw this hyperbola, you can look at here, as you go away from the surface, your graph will be like this. Okay, 1 second. Note it down, please. This is your axis of R, and this represents E out. E out is 1 over R square. Okay. This represents the surface. You can look at here. This represents center. Okay. This represents inside, spheres inside. Are you understand or not? Hello? Hello?
Yes, sir.
All of you understanding here?
Yes, sir.
Any issue?
No, sir.
This is value of E of S. Okay. Note it down, please. This represents sigma over epsilon naught. And this region represents R is greater than capital R, which is outside. Note it down, please. Have you noted it?
Yes, sir.
Hello,
Yes.
Nawal and
Yes, sir.
Matthew. Have you noted it? Okay. Okay. Next point, I mean, next heading we are going to discuss now. Electric field due to solid non-conducting sphere. We means we are going to discuss this condition. I mean, second one condition. You can write here electric field due to solid non-conducting sphere. Now we have taken here non-conducting sphere. Okay. Consider a sphere like this of radius capital R having charge plus capital Q. We can consider that the given charge is uniformly distributed throughout the sphere of radius R. Note it down. Charge Q is uniformly distributed throughout the volume of sphere of radius capital R. All right. Now, once again, we are going to do the same thing. First, we will calculate the value of electric field outside of the sphere. Then in the second case, we will calculate at the surface of the sphere. And in third case, we will calculate inside the sphere. Okay. So in the first case, outside of the sphere. Outside of sphere. First, we draw the diagram for outside. This is your sphere. Radius is R. Charge is uniformly distributed throughout the volume of the sphere. And we are going to calculate the value of electric field at any point outside of this sphere. Suppose that this is your Gaussian surface for outside of the sphere. This is your point where we want to value of the field. This is your electric field value, and the area vector also be in the same direction. Radius of this Gaussian surface is taken as small r. This is your center O. Okay. In the first step, we are going to calculate the flux through a sphere, which is phi is equal to integration of E dot ds cos 0 degree, which is phi is equal to E integration of ds, which is E into S. After taking it S, the value of S is 4 pi r square. 4 pi r square. This is your value of flux. Using Gauss law, your value phi is equal to Q enclosed over epsilon naught. Okay. What is your value of phi? This is your E into 4 pi r square is equal to Q enclosed over epsilon naught, which is E is equal to Q over 4 pi epsilon naught r square. This is the value of electric field outside of the sphere. In terms of volume charge density, or you can say in terms of density. We can consider the density is equal to Q over volume, I mean charge or volume, where Q is equal to density into volume is 4 by 3 pi r cube. When you put this value of Q into the equation number 2, we get put equation 3 in 2. You get E is equal to sigma 4 by 3 pi r cube over 4 pi epsilon naught r square. Pi is cancelled with pi and 4 is cancelled with 4. You get E is equal to rho r cube over 3 epsilon naught r square. This is your value of electric field in terms of density. Note it down, please. Have you noted it? Hello.
Yes, sir.
Okay, good. This is your value of a field outside of the sphere. Okay. In the next step, field at the surface. Okay. At the surface. We know that for the surface, we can easily calculate if we take this just 1 second. First, we should draw the diagram here. Then we will solve it. This is your radius R. And we are going to calculate the field at the surface now. When you will calculate the field at the surface, then just like in previous case, your small r, I mean radius is capital R is equal to the small r. We can take it or not, Matthew?
So
Once
we
again,
take it.
we can take it again is small r. Just similarly, we can consider here small r is capital, small r and capital R is same. And what is the last equation which we have calculated? Sigma r square, rho r cube over 3 epsilon naught r square. Value E at the surface is rho, what is your, 1 second, capital R cube over 3 epsilon naught small r square. And we have small r, sigma over sigma into r cube 3 epsilon naught small r square can be written as capital R square. After solving it, you get E is equal to rho into R over 3 epsilon naught. This is your value of electric field at the surface of this sphere. Note it down, please. All of you are understanding what we have, doing the change in the last equation. We have placed only capital R at the position of small r, okay, and we have reached at the surface of the sphere from the any point of outside. Are you clear? Hello?
Yes, sir.
Yes, sir. Understood.
Good. And now in the next case, we are taking here inside of sphere. Inside of sphere. This is your sphere of positive charge. Capital Q. And the radius is capital R. We are going to take any point inside the sphere. Then you should draw a Gaussian surface with respect to that point. And the radius you can take at small r. Now, as you have seen in the last case, inside of the hollow surface, if it is, then your electric field is 0. But in this case, it is not a hollow. Okay, it is a non-conducting. For conductor, electric field is 0 inside the surface. Inside the conductor. But in this case, it is not a conductor. It is a non-conducting body. So the net electric field inside this never be 0. Now, what will be the actual value of the field here? Let's try to calculate it. Consider a Gaussian surface of radius r. The value of flux is integration of E dot ds your phi is equal to again E into 4 pi r square. This is your equation number 1. And now using Gauss law, phi is Q enclosed over epsilon naught. And now, can you tell me the total charge enclosed is less than or greater than capital Q? Because we have taken a small area inside the sphere, not all. Okay, so we can consider here your Q enclosed is less than the capital Q. Okay, if Q enclosed is less than the capital Q, then what will be the amount of the volume of this capital Q charge? So you can write here Q enclosed is the charge on volume 4 by 3, 1 second, 4 by 3 pi r cube, where we are taking a small r. I mean, this is Q enclosed is that amount of charge. I mean, that amount of enclosed charge, okay, which is laying in radius small r, not in all of the radius capital R. Are you understand it or not? Hello?
Yes, sir.
Yeah, okay. If rho is the if density is uniform, density is rho. If density is uniform, then what will be your volume charge density? What will be volume charge density? It will be Q enclosed is equal to density into 4 by 3 pi r cube, which is your equation number. You can take it 2 and you can take it 3. When you put this value of 3 in equation number 2, then we get put 3 in 2. We get phi is equal to rho 4 by 3 pi r cube over epsilon naught. Okay. What is the value of phi? Put the value of phi here. E into 4 pi small r square, which is equal to the rho 4 by 3 pi r small r cube over epsilon naught. 4 pi is cancelled with 4 pi and r square is cancelled with here. You get E is equal to rho into r over 3 epsilon naught. This is your value of electric field for radius small r inside this sphere in terms of density rho. Are you clear or not? Hello? All
Yes,
of you
sir.
are clear or not?
Yes, sir.
Okay, note it down, please. It's noted or not?
Wait, sir.
Okay.
Noted, sir.
Okay, good. Nawal, have you noted it?
Yes, sir.
Okay, good. And now, how many equations are here? There are total 3 equations which we have calculated in this heading. First one is E outside, which is your rho r cube over 3 epsilon naught r square. The second value, E at the surface, which is rho r over 3 epsilon. And the third one is E inside, which is rho r over 3 epsilon. Are you understand? Rho r over, yeah. Are you understand these values? These values, these three values. Now, in all of these three values, okay, there is a single value. You can look here, E inside, which is equal to the sigma, rho r over 3 epsilon. Are you understanding or not?
Yes.
Are you understanding? Okay. And the second one at the surface, rho r over 3 epsilon. Then can you tell me, for this equation, we are taking this equation here, we can write E is directly proportional to the R. Can we say it or not? Hello? Hello? Nawal and
Yes.
Matthew, are you understanding this or not? Can we write it?
Yes.
Yes, sir.
Because E inside is directly proportional to the R. And when E is directly proportional to R, then we can say that the graph for this will be a straight line. Do you remember or not from your previous classes?
Yes, sir.
Okay. But okay, no need to write here till now. Okay, wait please. And in the next equation, which we are taking now, E outside, this equation. In this equation, your E is inversely proportional to the R square. Are you clear? In this equation, you can look at here. E is inversely proportional to R square. Then your graph will be hyperbolic like this. Are you understand or not? Okay. But we have already know. We have already know. And can anyone tell me at the center, what will be the value at the surface? Remember here, I am going to explain this equation in another way. Okay, try to understand, please. E surface, okay. Try to understand here. E surface is rho r over 3 epsilon. What will happen when we are taking, when r is 0? When we are taking r is 0, this means we are discussing here field at the center. Are you clear or not? Because at the center, your R is 0. Are you understand or not?
Yes.
Are you understand or not? For R is equal to 0, it means that we are discussing for center. At the center, when you put R is equal to 0 in the above equation, your value of E will be 0. And this is your at the center. Hence, we can say that from center to the surface. Remember here what I am saying. From center to the surface. From center to the surface. Your value of electric field is directly proportional to R. Am I right or not? Hello?
Yes.
Nawal. Nawal, are you understanding or not?
Yes, sir.
Tell me clearly, please. Are you understanding?
Yes.
Okay. From center to the surface of this sphere is directly proportional to R. This means as we go from center to the surface, electric field is increasing. Electric field is increasing. Are you clear? For this value, electric field is increasing as we go up to the surface. But when you go away from the surface, suppose that this is your any other point P, which is your outside. Okay, I mean, for this equation, you can look electric field is decreasing in what way? In what way? In hyperbolic way. This means we can say now your electric field is decreasing in like this way. Are you clear or not? And when you draw coordinate frame, then you can look the graph like this. Okay, and now I am going to draw the graph. Please note it down. One minute. One minute. I am going to take another page. This is your sphere. This is your of radius R. If you draw a straight line from this, your graph will be along a straight line till the surface. You can say till the surface, your graph is a straight line. And now, Nawal, can you tell me this? Okay, which one equation will satisfy this graph, this green line graph? This is for which equation? E outside, E surface, or E inside?
Outside.
Sorry?
Outside.
E inside. Remember here, E is directly proportional to R. You can look this graph. Are you clear?
Yes.
Yeah. And now when we go away from the surface, then what will be the graph?
Surface.
This is the position of the surface. When we go away from the surface, then what will be the graph? Now graph will be like this. You can look at here. Are you understand or not? Because as we go
Yes.
away from the surface, E is inversely proportional to R square. And your graph will be hyperbolic. Then we can draw your hyperbolic graph. Like this. Are you clear or not?
Yes.
Note it down, please. This is your R is equal to 0. And this is your position where R is equal to R. And in this region, R is less than R. Here, R is greater than R. Note it down, please. Next one is Matthew. Any issue in this graph?
No, sir.
Okay, good. Note it down fast, please. Have you noted it?
Yes.
Good. Next one. We are going to solve some questions now. Note it down, please. Your question is, show that charge Q given to a thick metal plate distributed equally on both sides. Okay. And now what will be the it is a question in which it is saying that show that charge Q is given to a thick metal plate is distributed equally on both sides. Okay. First of all, we are going to take a thick metal like this, and we can consider that amount of charge capital Q is given to this metallic plate. Okay, this is your question. Amount Q is given to this thick metallic plate, and this charge is equally distributed on both sides. Okay, suppose that algebraically we can consider, let us consider that amount Q1 is distributed in this side and Q minus Q1 is in this side. Okay, then can you tell me what will be the direction of the field? I think inside the plate, what will be the value of electric field inside the place? Because it is saying that it is a metallic plate, and we have already know for metallic plate, the value of electric field is 0 inside, always. Are you clear? You can consider here the density is sigma 2 and density is sigma 1 for Q. Now, we know that inside the plate, E1 plus E2 is 0. Or you can also write E1 minus E2 is equal to 0 because both are opposite in direction. Then we can say electric field 1 is equal to electric field is 2. Due to a plane sheet, or you can say, due to a plane sheet, we know the value of electric field is sigma 1 over 2 epsilon naught. And similarly for this, sigma 2 is 2 epsilon naught. Both will cancel. We get again density 1 is density. Hence we can also say electric field on both sides is same. Density on both sides is same. If the density on both sides is same, then we can write for density we have already know Q over area. For sigma 1, we can write, one second, sigma 1 is equal to sigma 2. For sigma 1, we can write Q over A, because the charge for sigma 1 is Q1 and area is A. Similarly, for density sigma 2, it is the amount of charge is Q minus Q2, which we have taken here, over the area is same, A. You can look at here, area will cancel with each other. Q is equal to Q minus Q1. Sorry, Q1 is equal to Q minus Q1. After transferring Q1 from right hand side to the left hand side, you get Q1 plus Q1 is equal to Q, or 2Q1 is equal to Q, or you can say Q1 is equal to Q by 2. This means the value of Q1, we get Q by 2. Okay. If Q1 is Q by 2, then what will be Q minus Q1? Then Q minus Q1 can be written as Q minus Q by 2. Again, we get 2Q minus Q by 2. We get Q by 2. This is your value of charge on another side. Hence, we can say on both sides, the amount of charge distributed is equal in amount. Are you understand or not?
Yes.
Hello. Are you understand or not?
Yes.
Yeah. Matthew, any issue?
No, sir. I said yes.
Okay, note it down, please. Note it down, please. Have you noted it? Nawal, Matthew.
Yes, sir.
Now it's clear or not till here?
No, sir.
So in today's lecture, we have finished chapter 1, electric field and electric charge and field. Okay. Are you clear or not?
Yes,
And
sir.
from from next class, we will start the electric potential and capacitance, right? This chapter
Okay.
is over now today. Okay. From next class, we will start a new topic, electric potential. Then we will come on the capacitance. All right.